Okay, we're going to quickly go over Pascal's triangle notes. And the idea is that you can go ahead and fast forward if you missed some of the notes. This was taken over 2 days. So we're just going to do a brief overview here. So when you take a look at the notes, you'll notice that the first part of Pascal's triangle has been filled out for you. And there's a definite pattern that exists. And the pattern is that each of the blocks brings with it the sum of the blocks above it. So if I'm here on the ones, there's only one block above it, right? So all of those are going to have a value of 1. So when we talk about a diagonal, we're talking about either left or right. Both of them are the same. So when I get to something like 2, it's the addition of 1 plus 1, and that's how I got 2. To get 3, it's 1 plus 2. And then again, this is 3 from 1 plus 2. 4 comes from 1 plus 3. 6 comes from 3 plus 3. So we definitely have a pattern there. So the pattern that we see is that each row is the sum of the 2 blocks above the current block. Okay. So now that we have that, and of course, notice that our rows, our naming convention starts with row 0, and then it goes to 1, 2, 3, 4. So now that you've determined the pattern, take the blank Pascal's triangle and complete the blanks. And so that's this one that you guys will be working on towards completing. I do have one completed here in the back. My suggestion would be to go ahead and look up the completed Pascal's triangle for 20 rows, or you can take a screenshot of this one and go ahead and transfer it to yours. You will not be permitted to have electronic devices on your quizzes, so if you need any of these numbers, you do need to get it on yours. Okay, so this should be enough time for you guys to get a quick capture. Okay. So once it's filled out, why does each row start with a number 1? Well, because it only has one block above it that has the value of 1. Each row begins with 1 because it only has one block above it with the value of 1. Okay, so if we take a look here, this is 1 because we started at 1, but this is 1 because there's just one block above it, and that value is 1, so that just carries down. Likewise, this whole entire row, and then this diagonal as well. Even number rows have blank number of entries, and odd number of rows have a blank number of entries. Okay, so if I look at row 1, that's an odd row, and I have an even number of entries. Row 2, which is an even number, has an odd number of entries, so those are opposite. Even number rows have an odd number of entries, and odd number rows have an even number of entries. Describe the numbers in the second diagonal column on each side. Okay, so if we're looking at the second diagonal column, we're talking about this column right here, or you could look at it from this side as well, right? So there's something very special about these numbers, and you'll notice that those are just the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so these are the counting numbers. Find the sum of the numbers in each horizontal row and write it to the right of the row on your big Pascal sheet? What are the patterns that you see with the sums? Let's see here if I think I have. I do. I have the sums right here on my big one. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. And you'll notice it just continues on, right? I just do multiplied by 2 each time. The other thing that you want to notice too is that this is actually equal to 2 to the 0 power. Anything to the 0 power is just going to give you 1. This is also 2 to the first power. This is 2 to the second power. This is 2 to the third power. This is 2 to the fourth power. So you'll notice that my row number is my exponent. So this is row 1. This is exponent 1. This is row 2, exponent 2. Row 3, exponent 3. So my sums actually help describe what row number I'm in. You also might, after having studied geometric sequences, made a note that the sums are a geometric sequence. And that ratio is, of course, 2. So it's going to double each time. So let's go back to our questions. What are the patterns you see with the sums? They double each row. We could say it's a geometric sequence of R equals 2. That's my ratio, right? We already had that. Explain why you think that pattern occurs. Well, let's take a look at one here, right? What happens is when I'm given a number, so let's look at this 2 right here, okay? So the 1 that's above it goes down to add to get that 1 that's there, but then it also contributes to that 2. And this 1 contributes to that 2 and also contributes to the 1. So every row above it is used twice in finding the sum of the one below it. So let's look at this row, right? 1 is used 2 times, both for the 1 and then added to the 2 to get 3. 2 is used 2 times, once to add to the 1 to get 3, and then to add to the other 1 to get the other 3. And this is used 2 times as well. So each of the previous rows is used twice. Each of the, what did we call them earlier? We called them entries. Okay, so each of the entries in the previous row is used 2 times in calculating the current row. All right, look at the diagonal of the triangle. The first diagonal, those are our 1s. Okay, this is just a brief review. Second diagonal is our counting numbers. Remember, this is like day 2 now of the material. The third diagonal of the triangle is called triangular numbers. The consecutive blocks in that third row always add up to get a number that has a pattern. So we want to find the sum of the first 2 blocks, the second 2 blocks, etc. So I'm going to go over to this one, and I'm going to look at my third diagonal, which is going to be this one, or I could go with this one as well, right? But I'm looking for that third one. So if I take 1 and 3, that's my first 2, that's going to equal 4. If I take 3 and 6, that's going to equal 9. If I take 6 and 10, that's going to equal 16. So let's get those over here. 1 plus 3 equals 4. 3 plus 6 equals 9. 6 plus 10 equals 16. Well, what we notice is that each of these are actually perfect squares, meaning that if we took the square root of it, it would give us a whole number. So the square root of 4 is equal to 2. Square root of 9 is equal to 3. Square root of 16 is equal to 4. And go ahead and take a look at the rest of that third diagonal and you'll notice the same pattern. So what is the pattern? 2 consecutive blocks in the third diagonal add up to be perfect squares. Okay, the next one is the Fibonacci numbers. And I don't know if you remember this, we've studied this already, where you take each number is the previous two numbers added together. So we start with 1. There's really nothing to add to it, so 0 plus 1 is going to give me 1. So that second number is going to be 1. Well, when I take 1 plus 1, that gives me 2. 1 plus 2 gives me 3. 2 plus 3 gives me 5. 3 plus 5 gives me 8. That pattern also exists in the Pascal's triangle, believe it or not. So I'm going to go over here to this one, and I'm going to have to put a little 1 here so that we can get all of our blocks done. So if I take this and I go through this diagonal, I'm left with 1. If I go through this diagonal, I have another 1. If I go through this diagonal, I have 2. Through this diagonal, I have 3. So I'm adding up, right? I'm adding up what I have through those diagonals. This diagonal, I have 5. And this diagonal, I have 8. And it just keeps going if I continue that trend. Okay, so I'm taking the diagonal through and between each number of my first diagonal. So through and between each number of my first diagonal. Let me get a thinner pen here. Take the diagonal through and between. Take the diagonal through and between the first diagonal. Okay. And then we're talking about probability. I want you to go ahead and read through this whole thing, but it says if you have 3 coins, okay, if you have 3 tossed coins, so a coin, you're going to toss a coin 3 times, or you're going to toss 3 individual coins. Either way, you're going to look at the third row, and then those numbers will give you the probability. So let me show you what that looks like. So let's go to this one. If I'm on that third row, right, row 3 is this one right here. I have 4 options here. And that 4 options will tell me which ones I've got. So let me look at, I can have heads, heads, heads. There's only one way to do that. I could have heads, heads, tails. I could have heads, tails, heads. I could have tails, heads, heads. So there's 3 different ways that I could get 2 heads and 1 tail. Then I could have heads, tail, tail. I could have tail, heads, tail. And I could have tail, tail, heads. So there's 3 different ways that I could get my 2 tails and 1 head. And then 3 tails can only be done 1 time. So take a look. 1, 3, 3, 1. That's exactly the numbers that are in row 3. 1, 3, 3, 1. So if I flipped a coin 4 times, right? This is the next question is, can you find the probability for throwing 2 heads and 2 tails with 4 coins? Okay, or 4 tosses, either way. Well, I would go to row 4 and take a look here, and I'm going to have to break those down. So I'm going to do a row 4. Okay, so of course you would have 4 heads would be the first number. And then you would have 3 heads and 1 tail would be the second number. 2 heads and 2 tails would be the third number. 1 head and 3 tails would be the third number. And then 4 tails would be the fifth number. So in row 4, I have 1, 4, 6, 4, 1. And it says, what would I get if I had a 2 heads and 2 tails? Well, here's my option right here, right? And I would have 6 out of a total of, if I add all those up, 1 plus 4 plus 6 plus 4 plus 1, right? That gives me 16. So that's out of 16. So 6 out of 16 is going to be my probability there. 6 out of 16. Then the next question says, what is your sample space for 5 tosses or 5 coins? Well, my sample space is my total number of choices, just like I got 16 on this one. 5 is going to be 1 up from 4, so I'm going to double this, and I'll get 32. If I wanted to find my sample space with 10 coins, I would go ahead and take a look at row 10, which is this one right here, and then I have 1,024 is my sum on that. So 1,024 is my sum. Okay. All right, the next part that we're going to take a look at are combinations. This is actually a very fast way to go through and get our combinations. So I'm going to have us do 2 to begin with. The first one is going to be 8C4. So 8C4. And remember with our combinations, it's NCR equals N factorial over N minus R factorial times R factorial. So that's what we're going to use as our formula. And so 8C4 is going to be 8 factorial over 8 minus 4 factorial is 4 factorial times 4 factorial. So I simplified this a little bit. I went ahead and did that subtraction. So I know in order to solve this, I'm going to have to take that and unpack it until I get to my greatest common factorial, which is 4. This 4 is going to get knocked out, and I'm left with 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. 3 times 2 is equal to 6, so that goes away, and 4 goes into 8 twice. So 2 times 7 is 14. 14 times 5 is going to give me the value of 70. Okay, so there's my first one. The second one I'm going to do is 6C4. 6C4. And once we go through these, I'm going to show you how to do it on Pascal's triangle, and it's super, super easy. But I want to do the actual math so that you know that I'm not telling a story about this, right? So 6 factorial over 6 minus 4 factorial is 2 factorial, and then times 4 factorial. So this is 6 times 5 times 4 factorial over 2 factorial and 4 factorial. My 4's cancel out, and the 2 goes into 6 3 times. So I'm left with 3 times 5, which is equal to 15. So 15 is my answer there. All right, let's see how to do it using Pascal's triangle. So 8C4, 8C4. That 8 is going to be my row number, and the 4 is how many spots beyond the 1 that I go. Okay, so 8, here's my row 8. This one gets ignored. Now, if you want to call it 0, you can call it 0, because that's essentially what it is. So row 8, 0, 1, 2, 3, 4. 8C4 is 70. What did we say it was up here? It's 70. Much faster to read the rows. So I'm going to go ahead and put down here 70. Now we said this one was going to be 15. So 6C4. So row 6, and then 0, 1, 2, 3, 4, 15. What did we get over here? Also 15. So my answer there is 15. All right, let's try 9C6 together. I'm going to abandon actually doing my computations. You can keep doing them if you want to check your answer. But 9C6. 9 would be row 9. 0, 1, 2, 3, 4, 5, 6. That should be 84. And then 8C5. 8, 0. 1, 2, 3, 4, 5 will be 56. 10C6. 10C6. So row 10 and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 210. And then the last one is 5C3. Row 5, 1, 2, 3. That would be 10. Okay, so I want you to go ahead and pause the video and see if you can go ahead and go through and find those combinations. All right, let's go ahead and go over those numbers. This 12C6, this is why we had you go ahead and build this one, because on row 12, you would have to go in to 6 positions. So 1, 2, 3, 4, 5, 6. 924 would have been your answer for that one. So I have 924. 5C2, you should have gotten 10. I think we did that up here. That was 5C3. 9C7 should have given you 36. 15C5, that should have given you 3003. Again, that was from your made up one because we had to go down to row 15, and we're going in from 15 over 5. So 1, 2, 3, 4, 5. Okay. And then 10C4, that one was 210, and 7C1 was 7. Okay. All right, how would you go about finding the numbers in the 100th row? Well, it's easy if you have your 99th row. If you know that 99th row, all you have to do is take the two numbers above it and add those together to get the numbers for that 100th row. But if you don't have the 100th row, since we know that the combinations exist, you could go ahead and get those numbers from your combinations. It'd be a lot of math to do, but it'll give you the answer. So I could do 100C1, and that would give me the first one. And then I could do 100C2. And then I could do 100C3. And on until I got all of the numbers in that row. Okay, another pattern found in Pascal's triangles is powers of 11. And can we find those? Powers of 11, get ready for this. 11 to the 0 power is this one right here. 11 to the first power is this right here. So 11. 11 times 1 is going to be 11, right? 11 to the first power. 11 squared is 121. 11 to the third is 1,331. 11 to the fourth, 14,641. So those powers of 11 exist as those numbers appear. Okay. The hockey stick pattern. These are looking for sums of numbers in a downward diagonal, and they don't always have to be in small groups. So I will show you 2 hockey sticks, and then you can come up with your own. So an example of a hockey stick might be, let me go ahead and grab a color here. I might have 1, 2, and 3, and then it adds up to be 6. So that would be the equivalent of a hockey stick. I could also have, let's see here if we've got another one. If I go from row 6, 1 plus 7 plus 28 plus 84 plus 210 is equal to 330. Okay, so that's another hockey stick. I probably should put that in a different color so that we can tell the difference between that and the green piece that's right there. Okay, so see if you can find some more hockey sticks, and those are the patterns that we're finding from Pascal's triangle.